Welcome to the practical workshop on software-based simulations. Today, we will use digital twin environments, similar to ETAP or Power Factory, to model extreme transient frequency events. Before we can test the grid's resilience, we must build the mathematical model. You are looking at a simplified single-line diagram representing two synchronous generators feeding an industrial load center. We initiate the Newton-Raphson load flow algorithm. The solver converges. Generator 1 and Generator 2 are each supplying exactly 600 megawatts to satisfy the 1200 megawatt demand. Because mechanical power input perfectly matches electrical power output, the grid frequency rests at a perfect 60.0 Hz. This is our steady-state baseline. Now, we transition from steady-state to transient stability analysis. We will solve the differential equations of the generator rotors in the time domain, step by millisecond step. We will introduce a severe n-1 contingency. At simulation time t equals 400 seconds, we will artificially trip generator 1 offline, instantly removing 600 megawatts of supply. Generator 1 trips. The grid is instantly deficient by 600 megawatts. Watch the frequency chart closely. To make up for the missing power, physics forces generator 2 to convert its physical rotational momentum into electrical energy. As it sacrifices kinetic energy, it physically slows down. The grid frequency plunges. We monitor the rate of change of frequency, or ROCOF. Because generator 2 has a high inertia constant of 5.0 seconds, the drop is smoothed out. If inertia were lower, the grid would collapse instantly. The frequency crosses 59.5 Hz. At 59.2 Hz, the system hits its lowest point, known as the nadir. If it drops to 59.0, under-frequency load shedding relays will automatically. But before UFLS triggers, generator 2's mechanical governor senses the speed drop. It commands the steam valves to open wider. Primary frequency control arrests the decline. Generator 2 is now outputting its absolute maximum of 1200 megawatts. The generation and load are balanced again, but the frequency is stuck below 60 Hz. This is the steady-state error. To restore the system clock, the grid operator's automatic generation control, or AGC, steps in. It slowly adjusts the generator setpoints to push the frequency back to exactly 60 Hz. This is secondary control. The simulation shows the frequency fully recovered. By modeling these transient events in software like ETAP, engineers can tune governor settings and size inertia requirements before a real disaster strikes. This concludes the software simulation workshop. Understanding the delicate dance of inertia, ROCOF, and governor response is the key to preventing cascading failures.